Welcome! Today we are deconstructing one of the most elegant and enduring pillars of computer science. We will move beyond basic syntax to explore the mathematical beauty of the divide and conquer paradigm, the critical importance of stability in data engineering, and the sophisticated optimizations like Timsort that power the software you use every day. To understand efficiency, we must first understand limits. Imagine a game of Guess Who with your data. In the comparison model, we can only ask if one item is smaller than another. Information theory dictates that to distinguish one specific sorted order from all possible permutations, the decision tree must have a height of omega of n log n. Merge sort is mathematically optimal because it hits this ceiling exactly, never wasting a comparison, unlike Quicksort, which can degrade catastrophically under bad conditions. Beyond speed, we need stability. Stability means that if two items are equal in value, their original relative order is preserved. Imagine an Excel sheet of financial transactions. If you sort by date first and then by amount, a stable sort ensures that transactions with the same amount stay chronological. An unstable sort, like Quicksort, would shuffle those dates randomly. For complex database operations, stability is not a luxury, it is a requirement. Merge sort follows a strict three-phase military strategy known as divide and conquer. First, we divide the problem space geometrically, splitting the array strictly in half. Second, we conquer by recursively applying the same logic to these smaller subarrays until they are trivial to solve. Finally, and most importantly, we combine. We take two perfectly sorted small lists and zip them together into one larger sorted list. This merge step is where the algorithm gets its name. We can express this behavior mathematically using a recurrence relation. The time t to sort n elements is equal to 2 times the time required to sort n over 2 elements, that represents our recursive calls, plus c times n. That last term, c times n, represents the linear work required to merge the data back together. Because the work is distributed evenly, the Master Theorem tells us this resolves to a complexity of theta of n log n. If we visualize the execution as a tree, we see a beautiful symmetry. At the top level, we process n items. One level down, we have two processes handling n over 2 items each, but the total work across that level is still proportional to n. This pattern holds for every single level of the tree. Since we divide by 2 each time, the tree has a height of log base 2 of n. Therefore, if every level does linear work, the total work is simply n times log n. Here is the classic recursive implementation in Python. Note the elegance. The function calls itself for the left and right halves. The base case, the anchor that stops the recursion, is when the list length is 1 or 0. However, in production systems like C++ or Java, we avoid creating new list objects like you see here. Instead, we pass integer indices to manage a specific range within a single existing array to save memory. There is no such thing as a free lunch. The price we pay for merge sort stability and worst-case guarantee is memory. Standard merge sort is not an in-place algorithm. To merge two lists, we generally need a third buffer to hold the result before copying it back. This means if you are sorting a 10 GB dataset, you generally need another 10 GB of RAM available. This space tax is its primary disadvantage compared to Quicksort. In the real world, constants matter. While merge sort is superior for large datasets, the overhead of function calls and memory allocation makes it slow for very small lists. Industrial implementations use a hybrid approach. When a subarray shrinks below a threshold, typically around 32 elements, the algorithm switches to insertion sort. Insertion sort is technically O of n squared, but on tiny arrays, it is blistering fast due to CPU cache locality. This brings us to Timsort. Developed by Tim Peters for Python, and now standard in Java and Android, Timsort is the apex of recursive optimization. It is not just a theoretical algorithm, It is an engineering marvel designed to exploit the non-random patterns found in real-world data. Timsort works on the assumption that your data is rarely perfectly random. It scans the array looking for natural runs, sequences that are already sorted. If it finds a descending sequence, it flips it. If a run is too short, it uses insertion sort to bulk it up. Crucially, during the merge phase, it uses a technique called galloping. If one list is consistently winning the comparison, Timsort switches to exponential search to move huge chunks of memory at once, drastically reducing CPU cycles. Is it possible to have it all? Can we have the stability of merge sort, the speed of n log n, but without the extra memory cost? This is the frontier of sorting research, in-place merge sort. Algorithms like GrailSort and Quicksort achieve this holy grail. They perform a magic trick. They use a small section of the array itself as a temporary buffer. They treat the data as blocks, swapping and rotating these blocks into position mathematically without needing external RAM. While extremely complex to implement, they prove that the space-time trade-off is not an absolute law, but a constraint we can bend with sufficient ingenuity. Finally, we must consider the hardware. Quicksort generally beats merge sort in RAM because it accesses memory linearly, playing nicely with the CPU's cache prefetcher. However, merge sort is the undisputed king of external sorting. When you need to sort 100 terabytes of logs that don't fit in RAM, you cannot jump around randomly. Merge sort's sequential access pattern allows us to stream data from disk efficiently, making it the backbone of big data frameworks like Hadoop. In conclusion, no single algorithm is perfect for every scenario. Merge sort offers guarantees and stability. Quicksort offers raw speed and RAM. Timsort adapts to real-world data structures, and block merge pushes the boundaries of memory efficiency. Understanding these trade-offs is what separates a coder from a computer scientist.